Swayam Prabha. Digital India. Educated India.
Welcome. So, we are in module 4. So, this lecture I plan to take beam column theory and its finite element formulation, especially the geometric stiffness matrix. The geometric stiffness matrix is also known as the stability matrix. So, what I planned is that initially I will just discuss about little bit of in brief theory, and then our main objective here is to find out the Euler buckling load. Now, Euler buckling load or the critical axial load on a column or a beam column structure, that is our finding out the beam column axial load or the column axial load or the Euler buckling load. The main objective is to find that. Now, also in doing so, we need to do the we need to derive the geometric stiffness matrix, and then I will discuss a small problem today. Now, to start with, we need to understand what is beam column. Now, we all know beam theory. Beam column problem, what is the basic premises of beam column. So, if we have found out the curvature, it's a curvature expression we all know. So, I will just briefly discuss it here. So, probably some of you have already read. So, the curvature formula, the exact curvature we write is 1 by rho is the curvature is d2w dx2 divided by 1 by rho equals to d2w dx2. So, w is the deflection. Now, that is equals to 1 minus dw dx whole square to the power half. So, this is also we know. Now, if you look carefully, there is a column. Suppose I take a simple column, okay, cantilever column, and then there is a force, axial force. Then the deflection of any intermediate point, the deflection will look like this. So, this is the deflection. So, now what will happen in the process? We have to consider the axial shortening of the column. So, that's the where this theory is actually differing from the standard Euler-Bernoulli beam theory. So, in Euler-Bernoulli beam theory, we also we generally assume that beam is inextensible, or the axial deformation of the beam is neglected. Now, here when you have a axial force, you have to consider the axial shortening of the column. Now, to consider that, we also need to do the uh, uh, axial shortening of the column. So, axial shortening of the column, how we can find out? So, suppose there is a force P, then integral 0 to L du dx is my axial strain, and then dx. This is the total axial shortening of the column. Now, in doing so, if I assume that column is incompressible, then from the theory I can establish a relation which is essentially 1 plus du dx whole square plus dw dx. If I assume that column is incompressible, that means that volume change is not permitted. So, that is equals to 1. So, from this relation I can actually transfer this du dw to du dx to dw dx. So, this if I write, then this axial shortening, if I substitute it here, then it will look like something like this. This is 1 minus dw dx whole square. This is root over minus 1. So, this is my axial shortening. Now, this axial shortening we have to consider in the theory. So, that is why if we consider this axial shortening, then what is the corresponding potential energy? So, potential energy or the strain energy essentially will have two components. First, due to the axial force, that column will bend and it will actually shorten also. So, the bending strain energy that we all know. So, the bending strain energy if I write, then we all know that is EI d2w by dx2 curvature square, EI by 2 d2w by dx2 square. So, that bending term we all know. Now, this axial shortening we have to consider the axial force. So, there is a again the displacement, axial displacement, which is the x displacement or the vertical, here it is vertical. So, this vertical displacement we have to represent in terms of that transverse deflection. So, now we always assume that it is a small strain or small strain theory. So, the small strain comes from here, that is dw dx is actually much less than 1. So, this assumption, so this is assumption again, okay. So, I think all of you know this from the your beam bending theory. So, if I assume this, then I can approximately write the curvature, that is approximately equals to d2w by dx2. And if I expand this the second equation, this is the first equation. So, these are the exact form, and the second equation if I do, then this second equation will have of this form. So, integral 0 to L du, this is obviously is a total shortening du dx integral over x. So, this is total shortening. So, if I expand this in series, so to the power half and then cancel this term, then what I will get is minus integral 0 to L. So, 1 will cancel. So, half will be there. So, now I will have dw dx whole square plus other terms. So, now since this quantity is again I assume this is small. So, higher order terms I am neglecting. So, this is my approximation. So, now this total shortening, due to this total shortening, there will be a potential energy. So, or the strain energy. Now, this strain energy again will have two components. So, first component of the strain energy is standard bending strain energy, that is your integral 0 to L EI by 2. So, we all know this d2W by dx2 whole square dx, and then there will be an additional axial strain energy. So, this how should I calculate the axial strain energy? The simple form for the axial strain energy is that let me write U axial. So, this is just for your understanding. So, P is the force. So, P into displacement at x equals to L minus displacement at x equals to 0. So, this is my axial strain energy. Now, this is equals to your P integral of 0 to L du dx into dx. Now, again this axial strain energy, if I substitute this equation, the approximating equation, then this is nothing but minus P by 2 integral 0 to L dw by dx whole square dx. So, now my axial strain energy will have another component, total strain energy will have another component. So, this whole square dx. Now, if I consider again it's a general term, so general beam, for instance, let us see a structure. Suppose if I consider a general beam horizontal, let us assume this is a general beam, and then let us assume there is an axial force. So, this can go down, obviously this is a roller. So, and there is a load, so Qx. So, this is actually true beam column. Now, if I have this, then obviously we will have a forcing term. So, again we will have 0 to L QW dx. So, this term will have this load. So, because of this there will be a vertical, here it is vertical. So, this is beam column actually. Now, this is the total potential, but we are not interested in finding out this kind of deformation of this kind of structure. Rather, we are interested in finding out the column buckling load. Now, so I will not consider this QW in this. So, that is not the objective. Now, when we find out the column buckling load, so we will consider only the potential energy of this form. So, this because there will be no force, so no transverse force obviously. So, now this is dw dx whole square dx minus P by 2 0 to L dw dx whole square dx. So, this is my total potential energy. Now, when I do the, I know how to do the Euler-Lagrange equation for this. So, if I take the first variation of this potential energy, then if I equate it to 0, then I will get the differential equation for the beam column and associated boundary condition. So, for instance, I am just, you can verify it. I am just writing the differential equation. So, the first term that will be there is standard the beam equation, that is beam part of it. So, d2 dx square into EI d2w by dx square. So, this is the term, and then we will have P into d2w dx2. So this will be 0 here because there is no force. Now if I consider the beam column, then obviously there will be qx here. So now let me also just write for this, the white one is for beam column. So d2 by dx square ei d2w by dx square plus p into d2w by dx square equals to qx. So again this is not the superposition is not valid, but again I will come to this thing later. So now once we have this equation, so this is just minimizing the standard potential energy of the beam column problem. Now here again we will have the boundary term also. So boundary term will also have the variational process will also generate the boundary term or the boundary conditions associated. So the boundary conditions are the similar to the beam problem, but only difference is that the first term is ei ddx of ei d2w by dx square. This is essentially the shear force, and there will be p dw dx. So this will be equals to either this has to be specified or this is the shear component of this thing. So in case of beam, this term is not there. So or w equals to 0. So either this has to be specified or this has to be specified. Now another boundary condition is ei d2w by dx2 has to be so let us not give this 0 right now because this is a general procedure. So either this has to be specified or this has to be specified, or the moment has to be specified, or the slope, that is dw dx, has to be specified. So this is the standard theory. So at x equals to 0 and L, any of the term can be specified. So we need 4 boundary conditions here. So essentially this is comprises of the beam column theory. Now this is column theory. Now the interesting thing is here that you really cannot so remember one thing, those who have read beam column, they probably know it. So this equation is essentially cannot be superposed. That is, if I solve the beam equation, for instance, d to the power 4w by dx to the power 4 equals to qx, and ei d to the power 4w by d, here I am taking ei constant, so plus p d2w by dx2 equals to 0. So this solution cannot be, this is not allowed here, okay, because this superposition is not valid here, okay. So remember this thing, this is in the mechanics class, this will be some of you may know, but remember this is not just a superposition like we did for the Euler-Bernoulli beam. If Q1 and Q2 are two forces applied on this, then superposition is allowable in the first equation, but these two superpositions are not allowed. So that doesn't support the theory. So that's the essence of this. Now our objective here is to find out this quantity, that is the critical buckling load or the Euler buckling load, P, the smallest load that actually create the or actually initiate the buckling of the column. So now this P if you look this equation, this is essentially an eigenvalue equation. So this is a homogeneous equation. This is an eigenvalue equation. So our standard finite element procedure. So now I am just moving to my standard finite element procedure. So let us take EI constant. So EI, so my governing equation is d to the power 4w dx to the power 4 plus p into d2w dx square, that is equals to 0. So this is my equation. So my standard weak form is this. Integral, if I choose weight function v, then integral 0 to L v into EI d to the power 4w dx to the power 4 plus p into d2w by dx square into dx. So that equals to 0. So that is my standard weak form. So now if I just do integration by parts, then what will happen? I will get the stiffness matrices, and there will be an extra term that will coming from this p d2w dx2. So this term I will do 2 times integration by parts, while this term I will do 1 times integration by parts. So if I do 2 times integration by parts, so what I will get is 0 to L d to v dx square EI d2w dx square dx, and for this there will be a minus. So integration of 0 to L p dw dv dx and dw dx. So this is 2 times integration by parts, and then for this there will be a boundary conditions. So the first boundary conditions will be plus which will be your w this v of x into ddx of EI, or you can directly write since I have taken EI constant, so you can directly write EI d cube w by dx cube. This is at x equals to 0 to x equals to L. So this is the first term. So you see that there is a shear force term and there is this term, and then you will obviously have another minus which is dv dx, and you have moment, that is EI d2w by dx square at x equals to 0 and x equals to L. And then for this there will be another boundary condition. So this boundary condition will have let's say okay, so this will have plus, so that is v of x into d w by dx. So this is at x equals to 0 and x equals to L. So this is equals to 0. So now if I rearrange this, so this is the bending part of the potential energy, that will generate my finite element beam stiffness matrix, the discretization of which, and then p is not a function of x because p is unknown here. So p I can take outside. So that is dv dx and dw dx. So this is 0 to L. This is dx, and then if I add this term, so that is vx into this is vx into EI. I just want to so here there will be P. I forgot to write a P because there is a P term here. So P dw dx. So here what I will have is this term, that is EI dw d cube w by dx cube, plus here I will have P into dw dx. So this whole term is the corresponding shear force term. So x equals to 0, x equals to L. Then here there is that standard slope, and so if you remember these boundary conditions are coming, if you can see. So this is d2w by dx square. So this is at x equals to 0 and x equals to L. So this is equals to 0. So these are the boundary terms. So this so in case of a beam, so simply if you put P equals to 0, then this is the beam weak form. So now when P is non-zero, and P we need to find out to compute the critical buckling load or the Euler buckling load, then this term will generate our standard beam stiffness matrix. So, and this term will generate my stability matrix or the geometric stiffness matrix. Sometimes it is also in case of a building frames where the beam column structure is there. So if you want to consider the nonlinearity of the structure, then P delta, it is also known as the P delta effect. That is, because of the deflection in the transverse direction, there will be an axial shortening of the column. So this effect is also known as the P delta effect. So that P delta effect requires to compute the geometric stiffness matrix. So the standard beam shape functions, we are familiar with beam shape functions right now. So let me just rewrite it again. So if you have gone through it, phi 1 is 1 minus 3 x squared by, I am just writing in x and L, so not so this can be modified for x bar and L. So that is plus 2 x cube by L cube, then phi 2 is my minus x into 1 minus x by L, phi 3 is my 3 x squared by L square, then minus 2 x cube by L cube, and then phi 4 is my, so if you remember, this has come from the Hermite interpolation. This is not a Lagrange interpolation because slope continuity, requirement for slope continuity. So now this is minus x into your, so this is square, so 1 x squared by L squared minus x by L. So this is my beam shape function. So now the Wx or deflection I can assume like this: phi 1 W1, phi 2 W2, or theta 1 plus phi 3 W2 plus phi 4 theta 2. So this is my finite element approximation for element. So if I just write for the same two-noded finite element, so here I have this, and this. So that is W1, W2, theta 1, theta 2. Now here I have the length is L. Now for this, if I now substitute this thing, so this will lead to my Keij, that is the beam stiffness matrix, which we all know, but let me just rewrite it. So d phi I phi j into d2w, obviously, So EI d2 phi j dx2 dx, and this will lead to my beam stiffness matrix, which is Ke, elemental beam stiffness matrix. So 2 EI by L cube, so that is equals to 6 minus 3L minus 6 3L, so this is 2L square, then 6 minus 6L, then 2 then this is L square, then this is 6 3L 2L square. So this is my beam stiffness. So this is a symmetric matrix. So this is my beam stiffness matrix that we have derived. Now the second term, that this term is required to find out. So that will generate my geometric stiffness matrix or the stability matrix. Now let us define the stability matrix as Kg. But remember, this is a elemental stability matrix. So K geometric stiffness matrix Kg. Now this, if I write Kgij, then this will give me d phi I dx into d phi j dx into dx. So this will give me the, so this term. So since P is my unknown, so that's why I do not consider P. So now this will give me my geometric stiffness matrix. So my geometric stiffness matrix will look like, so now you can take the first derivative of phi 1, phi 2, phi 3, phi 4, and then compute the corresponding term. So if you look, this bilinear form is also symmetric. So again the geometric stiffness matrix will be a symmetric matrix. So then this will be 1 by 30L. So this again is a symmetric matrix. So let me just write it. So this is 36 minus 3L minus 36, 3 minus 3L, then this will be 4L square, then it is just an integration, so you can check it, the entries. So 36, 3L, and then this is 4L square. So this is my symmetric matrix. So now likewise, if I now come back to the this equation, so this is my standard weak form. Now these terms are the boundary terms. So these terms will generate my boundary equations. So that will go to the fourth side of the equation, and this term will obviously give me the stiffness term, including the geometric stiffness. So let me, the other procedure is very simple. So again you will assemble it as per the finite element discretization. So once you assemble, you get the global stiffness matrix, that is K, and then you will have PCR or P, let me write it PCR, critical. So that is your PCR, and then you will have the global geometric stiffness matrix. So this will be multiplied by your global vector, which will be W, but W is a general vector. So if I write it the element wise equation, then it will look like this. The element equations are K element stiffness matrix, then PCR into your Kg elemental stiffness, then that multiplied by your W1 theta 1, W2 theta 2. So this is my elemental equilibrium. So again we will have Q1 boundary terms, Q1, Q2, Q3, Q4. So this is my equivalent equation. Now since our objective is to find out the PQR, the P critical, that is the Euler buckling load, so we will not think about this thing. So the boundary term will go to essentially 0 from the boundary condition. So again this equation after assembling, so here if you do assembling for all elements, then you will get the global stiffness matrix, then P critical, so Kg geometric stiffness matrix, then you will have your vector of W, then you will have your global degrees of freedom. Now here remember that PCR is the P critical. So suppose in a column you discretize with 10 elements, so 10 or 11 nodes, 10 element, 11 nodes. So the total degrees of freedom in your structure will be 11 into 2. So some of the points will be obviously specified, some of the degrees of freedom. So the total number of the buckling load will be the total number of the degrees of freedom you have considered, because this eigenvalue problem is dependent, this eigenvalues will be dependent on the matrix sizes. So matrices will be 22 by 22 for if there is an 11 degrees of freedom, and Kg will also be a this is also a 4 cross 4 matrix. So Kg will also be a 22 into 22 matrix. So obviously some of the degrees of freedom are specified and you have to put the boundary condition. Then you get you solve the eigenvalue, standard eigenvalue problem. So we are interested in the smaller eigenvalue which will represent my Euler buckling load or the critical buckling load. So that's the overall theory. So it is very similar to the frequency domain analysis or finding out the natural frequency and mode shapes of the beam structure that we discussed last time. So this is it. So I will just briefly mention the one example. You can check it. So we'll do some detailed example probably later. So suppose I wanted to find out critical buckling load of a simple column, cantilever column kind of thing. So here I have a P load. Now this column we know that deflection is 0 here and slope is 0 here. So if I just take one element, simply one element, we can find out the critical buckling load. So what I will do is that I'll use this equation. So if you look carefully, that is your so if I take my this thing, then this this term is 0 and this term is 0. So I will have just only in these matrices I will have this term and this term will be 0. So I will have essentially these two terms. So and there is no external force, so all boundary conditions, this Q2 and Q3 will also be 0. So if I just now write for this equation, this thing, so what will be our matrix form? So the matrix form will be 2ei by L cube, 2ei by L cube. So this is just one element. Okay. So this is 1, this is 2. Okay. So now the matrices will be 2L square minus 6L minus 6L 6 minus PCR and then you will have PCR by 30L into 4L square 3L 36. So this multiplied by theta 1 W2 equals to 0 0. So this is an eigenvalue problem. Now this eigenvalue problem, how we solve this eigenvalue problem? We solve through the we take the determinant of this term is 0. So essentially det of that is 2 EI, that is 4 EI by L. So we can write this, that determinant of this minus you can just do this calculation. So PCR by 30L into 4L square. So 4 into, so you can just compute this term. So determinant of this equals to 0. So that is the det of this matrix should be equals to 0, from where we get a quadratic equation of PCR. So this will generate a quadratic equation of PCR. So we will have two values of the two eigenvalues, that is lambda, and that is PCR1 and PCR2. So the smallest PCR that you can verify this, the smallest PCR that P critical is your 2.486 EI by L square. That is your smallest critical load. So this is a finite element solution with one element. Now the exact solution for this, or the exact buckling load for this problem, is P critical exact. If you look, then that is pi square by 4 into EI by L square. So that comes around 2.467 EI by L square. So if you see, this is my exact solution and this is my approximate solution. So these solutions are very near or very close to each other. So that's how we compute the Euler buckling load. So now this, if you refine this mesh, so if I now, instead of one element, if I consider 10 element or more number of elements, so this will closely approach to the first buckling, exact buckling load. So this is how we compute the frequency also. So that was the main objective. So in summary, the takeaway from this is that similar to the mass matrix that we have derived in your frequency domain, finding out the natural frequency, we will have a stability matrix or the geometric stiffness matrix. The same the point of finding out the geometric stiffness matrix is this. So this is my geometric stiffness matrix, and how we compute this. We compute like this, and then this creates an eigenvalue problem. So solving out the eigenvalue problem, we can find out the critical buckling load. So there are other methods also, for instance Rayleigh's quotient and other thing, so by which also we can compute the critical buckling load. So those are also approximate method. So and there is exact solution possible for simple columns, obviously. So that's how we know the exact solution. So that's all. So we'll meet in the next class in lecture 21. So thank you.